Okay, now we're going to dive into some modeling applications with differential equations. And we're going to illustrate some of the key ideas here using population growth models. Our objective in this video is to revisit the population growth models that we've explored before in Calc 1 as an application of modeling with differential equations. So we begin with the one that we know and love, and I'm using love here very freely. The Malthusian model. So a word before we talk about anything else, just because I think it's important to revisit math and realize that math is not neutral. So a note about Thomas Robert Malthus. So Thomas Robert Malthus is the mathematician who proposed the model that we're going to talk about here. So he came up with it, and he used it as a model for population growth, where he saw unchecked growth and thought that it was a problem. So for context, in the early modern period, the population of Europe exploded. Once the warfare of the 16th and 17th centuries calmed down, and then the last plague of literal plague in England in the mid 1600s, I forget. The point is that after that, it was a relatively calm time period, and the population grew very quickly in Western Europe in particular. And so Thomas Robert Malthus said he had a mathematical model for population growth, and his model suggested that the growth of people living on the earth would never stop. And that would lead to a problem which ended up getting called the Malthusian Trap. And so his model actually ended up leading to something called eugenicist thinking. Basically, there is not enough resources on this planet for everyone, and we need to think about ways of limiting who gets to live. And so he himself was not a eugenicist, at least not to my knowledge, but he did inspire some absolutely horrifying ideas in human history. This model, though, we can use it for things like bacteria, where like unchecked population growth is like, that totally makes sense. Just remember that in the long run, we don't extrapolate this model to like all human population growth. Like, it's just not, first of all, it's not accurate. Second of all, because it leads to eugenicist thinking. Anyway, enough about that. So the fundamental question here is, how does population P, and we could be talking about a small country, we could be talking about the whole human population, we could be talking about a different species altogether, grow over time, which will denote T, okay? And so the law of proportionate growth says, the Malthusian model basically, that dP dt is equal to Kp. This is a differential equation, and you might remember that this comes from section 3.8. We've talked about this before. And this came up in the context of exponential growth, right? So we know already what this model is giving us. In this case, our growth constant is a positive K, and the family of solutions has the form PC of T is equal to CEKT. Okay, C being a constant, right? That determines the different kinds of solutions, right? And so we can plot the family members roughly as such. So there's curves that look like this. And we're moving forward in time, so you want to think about this as having a direction, okay? We might call that the flow of the differential equation. That's beyond the scope of this course, so don't even think too much about it. But roughly, these are the kinds of curves that we could get, right? There's, of course, also the trivial solution, p equals 0, okay? So p equals 0 is a trivial solution. But maybe this is something like p of t equals, I don't know, 10 e to the kt for whatever k happens to be. And then the larger the initial value, right? Maybe this is 20 e to the kt. Then it grows at the same rate, but it starts out faster, okay? So here, though, let's think about what this model is actually giving us, because we need to be careful about what assumptions we can make about this model, right? So first of all, so only solution curves in Q1 are meaningful. Why? Well, we don't care about negative time, right? And we also don't care about negative growth, right? Because that would assume that k can be negative, and so that's not one of the cases that we care about here. So we're going to eliminate all those. And we're going to eliminate any negative time because we don't care about that. Okay. So then this reduces our model to this, right? Which is still, this gives us something to work with. So notice for all of them, p of t is increasing. And p of 0 being p naught gives us a predictably simple model. Okay, so at time t equals 0, you have the initial population. Okay, so you can write it more accurately as p of t equals p naught e to the kt. And so here's the important part about this model, which is where we get the Malthusian trap. The Malthusian trap is that the asymptotic behavior of any of these curves except for the trivial one, p equals 0, is infinite. So think about that in the context of Malthus's original proposition, which is that human population growth over time is unchecked and grows infinite, right? In practice, this is unattainable though, right? And it's just not, it's not a real representation of how population changes, right? So this model is only valid for small t, okay? So with that in mind, we can improve on this model slightly using what we call the logistic model. Again, these we're going to talk about in more detail later on, but basically we're going to start with the Malthusian model and we're going to improve on it. So we're going to change two key assumptions. So the law of proportionate growth, while it was good, it did not give us, in the long run, something that we actually wanted to. So we like that dp dt is approximately equal to kp when p is small. Okay, so if the population is small, then that's fine. That makes sense. But eventually, if p ever exceeds a carrying capacity, so this assumes that there's like a upper bound, a ceiling of population growth. So we can't go beyond a certain population growth or certain population size. Then we want dp/dt to become negative. And that's a reasonable estimate, right? So let's say you have a population with a finite amount of resources, food, shelter, water. If you exceed your carrying capacity, you no longer can provide all those things. And so the population goes down. This makes more sense in the context of when we're talking about observing populations of wild animals, for instance, right? So in the logistic model, okay, so thanks to Verhulst, hope I pronounced that right, we have the logistic differential equation, which defines the logistic model. Sorry, I had to suppress a sneeze just now. Okay. Then we have the differential equation, dp/dt equals kp times 1 minus p over m. Okay, so you notice that the difference here is that we're multiplying by this factor 1 minus p over m. And so here's the thing about this. So we're talking about p as a fraction of m. So notice that when p equals m, dp/dt equals 0. Okay, so in other words, when p equals m, when we're at our carrying capacity, we no longer change the population as a function of time. It stagnates. Okay. Now, whether we're coming from above or below, so in other words, if the population is below m, so we're just under the carrying capacity, it'll flatten out. And then if it's just above, right, it'll flatten down to that level. So this factor that we include is going to give us a family of curves that we're not going to give the full form of the solution family right now, but I am going to graph some representative curves for this family. I want you to pay attention to two interesting pieces here. So this time we're going to have two what we call stationary curves. Okay, so we have two equilibria. Okay. We have p equals m and p equals 0. Those are both equilibria. So these are solution curves that are constant over time. So these are also going to be limits, but we'll see that in a second. They're going to be horizontal asymptotes too. But we get some curves that look like this. So if we're below, so if our initial value is below, at, or above the carrying capacity, we get three different regimes basically, right? So we have three regimes of this model. So regime 1, which is what we call growth, and that happens if the initial population is at below the carrying capacity, right? We have room to grow, and this gives us the limit as t goes to infinity of p of t is m. So we slowly but eventually come to the carrying capacity and then stop. 2 is decline, where if the initial population is greater than the carrying capacity, we get a steady decline down to the carrying capacity. Again, we have the same limit. right? This time, P of t is decreasing. And lastly, we have the two equilibria, which I highlighted below. P equals m and P equals 0. So these are constant curves that are solutions to the dE. P of 0 is an unstable equilibrium, okay? And P equals m is a stable equilibrium. And roughly what you want to think about is curves tend to get closer to P equals m in the family of solutions, and P equals 0 is one that solution curves tend to move away from as you go left to right, okay? So there's some very deep ideas here, and we're going to talk about them in more detail later on. So we'll revisit these models